Hello, I am Eron and this is Noah. We work at Basecamp, which you might previously have known as 37 Signals. I work in operations and I'm kind of mostly focused on networking and monitoring. And we are here today to talk to you about chicken and waffles. So at Basecamp, we make Basecamp, which is a SaaS project management tool that's used by millions of people to get their work done. We've written a few books that you might have heard of called Rework, Remote, and Getting Real. We also made a little web framework called Ruby on Rails, but I'm not sure anybody really uses it anymore. Now, Basecamp is a little bit different from a few of the presenters we've had here so far and some of you in the audience. We're not a startup. We've been around for a long time in some form since 1999. We never took outside funding, and we've been profitable since we started. We're a very flat and almost entirely remote company. We've got about 50 people right now. And we own things. We own physical servers that sit in racks in 3 different data centers. We really love Nagios, and I mean it. And despite what Pete said last night, we actually run our own email servers. So we're also a little bit different because we got attacked. And usually when you get attacked, you don't talk about it. And you specifically don't talk about what you did to try to mitigate that attack and try to prevent future attacks from happening. But we're here today to do that. So we were all hanging out on a quiet Monday morning in ops when this happened. And that is never really what you want to see on your Monday morning in ops. So I went and looked at our nice internet dashboard, and we saw that all of our primary internet links had been quickly put to their max inbound bandwidth. And I went to my email account, and I saw this lovely note. Our good friend demanded 1.9 Bitcoin, which at the time was about $1,100 to stop this attack and any future attacks. We definitely were not going to pay this guy. And so let's talk a little bit about the attack and what it was that hit us. In terms of DDoS attacks, it was relatively small, and it was almost entirely a volumetric attack. The attack itself was measured at about 80 gigabits a second. Which was certainly more than enough to max out the 4 gigabits a second of transit that we had at the time. And there were a few different attack signatures that were used to try to take us down. The primary one was DNS reflection, which uses spoofed IP addresses to send packets to open DNS servers that force those servers to respond with packets that are much larger than the original request. And so with this kind of attack, you can amplify your available bandwidth by about 50 times. And it's stupidly easy to do. We saw a little bit of NTP reflection as well, which is basically the same thing, but it uses open NTP servers, and it has an amplification factor of about 200x. And we also saw some SYN floods, which is when you just open a ton of TCP connections to try to exhaust the TCP stack of whatever you're trying to attack. And we saw some ICMP, which is just tons and tons and tons of pings. So fortunately, we had NetFlow monitoring from our routers, which allowed us to see who and what was hitting us. So this is a view of the flows that we monitored over time from the attack. So you can see the initial burst was mostly DNS, which is the red line there, as well as SYN floods. And then we got the lovely demand email shortly after that. We didn't respond, so the attack started back up. And the graph here is over about a 2-hour timeline. That was how long the attack lasted. The attacker moved between different attack types to try and figure out what would work best to take us down. You can see the SYN floods. That portion of the attack was not as successful as the DNS portion of the attack, and so he shifted back to DNS traffic and moved around IP addresses, did a bunch of things. Throughout this 2-hour attack period in this graph, we were down for about 45 minutes, which is not ideal. So this caused us to get much more serious about our DDoS strategy, about defense and mitigation. And preparing for this kind of attack was actually the most straightforward part of what we did. We're really lucky to have a great data center partner that worked with us both to mitigate this particular attack and to prepare for future attacks. They were willing to put up filters for these kind of attacks because we don't take DNS and NTP traffic on basecamp.com. But we also went shopping. Rather than spend 2 Bitcoins, we spent a whole lot more money on a bunch of 10 gig circuits from multiple internet providers and some nice new router hardware to support those circuits and also to give us a little bit of a beefier presence at the edge. And we also worked with some outside vendors to get emergency access to sort of upstream cloud mitigation tools, just in case. But in the process, we also had to get more serious about more subtle application level attacks, which is what the bulk of this talk is really more about. These kind of attacks are like vulnerability scanners, slow login requests that try to exhaust resources on our pages, brute force login attempts, crawlers, and just other kind of nasty business on the internet. So to try and evaluate, or to try and tackle this, we evaluated a few commercial hardware appliances. These appliances sit on your premise, and you basically plug your internet into them and then take whatever they give you out of the back. And we had one of these. We ran with it in production for about a year. And we ended up being kind of frustrated with the performance and the maintainability and the reliability of this device. We had customers who reported kind of strange SSL problems that they would get from this device. The device was supposed to fail open, although that didn't really turn out to be the case when we had an actual problem with the device. And in the end, we really didn't get any measurable protection from it. The device uses kind of sort of like an antivirus model based on attack signatures. And in the end, those attack signatures just didn't match the kind of websites that we run. And so all of the alerts that it was sending were all spurious, and we didn't actually find much value from what we got out of it. So in the end, we decided to look into what kind of protection we could create on our own. And I'm going to bring Noah on to tell you more about that.
Thank you. So Eron is an operations guy. I'm not. I run data and analytics at Basecamp. So while he was dealing with the Bitcoin and the attack, I was hiding under a rock somewhere. But I do have PagerDuty on my phone, so hopefully that gives me a little bit of street cred. So after this attack and after we tried kind of the go shopping approach, I started to look at kind of what do we actually want and what could we do on our own to try to get us some meaningful protection. And so we came up with 5 things that really mattered to us. The first is, we really scoped the problem down to just be about these application level attacks. We felt reasonably good, knock wood, about kind of these volumetric attacks between the filtering and the circuits and the hardware and these vendor arrangements. And so we really wanted to focus only on these application level attacks, but to really get some meaningful protection from things that might attack our applications specifically. The second thing that was really important to us is we have a lot of actual users who just want to use our application. They just want to manage their to-dos and communicate with their team. And so it was really important to us that whatever impact any mitigation system we had on our actual users was really minimal. We wanted to take advantage of the fact that we know a lot about who our actual users are, right? We don't run any major public kind of unauthenticated websites. We run apps for people who have accounts and pay us money. And so we know a lot about who those people are and what normal traffic looks like. And so we can take advantage of that knowledge that a black box device that just sits and looks at request headers or unterminated SSL requests can't do. And so we wanted to really take advantage of everything we had. We wanted it to be really transparent in terms of who we were blocking and why. If we're going to block an IP address, I wanted to be able to tell the customer when they wrote in upset, or their IT team wrote in and said, why are you blocking us? I needed to have a reason that I could say, here's why we blocked you, here's what we can do to figure this out. And so that transparency was really important. And then I think like all good tech projects, the most important thing was that it had a great name. And none of the commercial options had great names. So we decided we needed chicken and waffles, and I'm not just talking about lunch this afternoon. So part of that is WAFFLES, which is the part of the system that carries out the actual blocking and filtering. which is it's a web application firewall, a WAF, from less expensive servers. And then chicken is kind of the brains of the operation. It figures out who do we want to block, what traffic do we want to filter, what are the threats we're facing, and what are the actions that we want to take. And so I thought for a long time about what chicken stood for, and then I decided that I would just give up and admit that it's a backronym, and hopefully the clip art would save the day. So I'm going to talk a bunch about chicken. And for chicken, the question is really simple. It's take a list of IPs and figure out which of these IPs represent a real user, right? And which of these IP addresses might be either a user with a broken API integration or someone who's actually malicious. So it's at its core a really fundamentally simple question, right? Bunch of IPs, who's good, who's bad. So I'm a data guy. You can call me a data scientist if you know what that means, though I don't. And if there are any other data people out here, you look at a problem like this and you say, this is just classification, right? You've got two groups, good and bad, right? And so all I need to do is figure out how do I classify IPs into good and bad. So, kind of your classic problem. So you take a bunch of data about IPs, right? You feed it into some sort of magical algorithm, right? You feed like your neural networks or your k-nearest neighbors or a support vector machine or something else, right? Like whatever, magic, right? You add some training data, right? You give it a set of, here are some good IP addresses, here are some bad IP addresses, and then out comes this magical answer, right? This IP is good, this IP is bad, right? This is like your classic machine learning classification problem. You can think of it like email spam detection if you want. There are a couple problems with this for us. So one is that a good training set when it comes to IPs is really hard to come by, right? You basically have two options. Either you've blocked a ton of IPs manually and you have a lot of data about those, and so that's your training set, or you're willing to look through 10,000 IPs usage patterns and manually classify them. I'm really lazy, so that didn't sound like a lot of fun to me. The other problem is that explicability problem, right? I need to be able to tell a customer why they were blocked if we accidentally block them. And saying like this black box algorithm that even I don't understand did it, that doesn't cut it, right? These customers pay us lots of money, and so we need to be able to give them a good answer. And so just having that answer alone of whether or not they're good or bad doesn't work for us. And then finally, I'm actually not very smart, and math is really hard. And so if I can avoid doing math or if I can just do arithmetic, that's what I'll do any day of the week. So we took a simpler approach, and it's just 3 easy steps. So one is, we know that there are a bunch of behaviors that we can observe that there's no chance that someone exhibiting these behaviors is a real normal user, right? So we run Rails apps at Basecamp. Obviously, we made Rails. We don't run any PHP apps. We don't run any Cold Fusion apps. We don't run a WordPress site. And so if someone's making a request for PHP MyAdmin, they're not looking for us, right? If someone's trying path traversal, which I don't know when the last time path traversal worked in a web app, they're not looking for us, right? Emily just a little bit ago showed those accounts with all the script tags. We get a lot of people named script alert, right? We also get a lot of user agents, interestingly, with script alert, right? Someone who has that isn't a user of our apps. They're someone who's up to no good in some way. So we can look at those behaviors. That's the first part. The second thing that we look at is we have the full request history for an IP, right? And so we can look at that request history and we can see whether someone's a normal user, right? A real user, but probably in some way broken, right? They have an API script that's doing something wrong, or they left a rock on their F5 key or something like that, or someone that's malicious. And for us, we're really lucky because our app is this authenticated paying app, that if someone has a history, if an IP address has a history of successful authenticated requests to a paying product, it's a pretty good indicator that they're a legitimate user. We also know that most legitimate users who are using our apps see a lot of 200s, they see some 302s, right? They don't just see 403s or 500s, right? They see a more normal set of status codes. And most users have pretty reasonable response times. We're an app, right? So we have parts of the app that are slow. There are page loads that you can find in Basecamp that will take a couple seconds to render on the server side. But that's not every page load. And so a user who every page load, they're finding a 30-second page, is probably not a normal user who's using Basecamp in a normal way. And then finally, we can look at a bunch of external indicators. So we know where our customers live, right? We know that most of our customers use either residential or business internet providers. They don't use VPSs or Tor nodes. So we have a good indication of who our users are, and so we can figure out whether an IP is more or less likely to be a real user. We also participate in Facebook's Threat Exchange, which is a collaborative way of identifying threats, whether IPs or other things. So we both use the data that comes from Threat Exchange and then also submit our results back to Threat Exchange. So these are the 3 things that help us to understand an IP and really get some understanding of who they are. So if we just talk at the first thing, so we've been doing this for a little over a year in terms of looking for these behaviors. In that time, we've got about 6,000 IPs that really just weren't very creative, right? These are people who either looked for phpMyAdmin, right? About half of them are doing that. You'd be amazed at how many people try to make HTTP requests using verbs that aren't part of the HTTP spec. People who just hammer away at the login form trying either totally random email addresses or totally random passwords. People who use vulnerability scanners and can't even be bothered to change the default user agent. And people who do things like put script as their user agent in case we have a cross-site scripting vulnerability that hits on user agent. So this is really kind of basic stuff. And the reality is that these aren't the threats that really worry us, right? The people who are so not creative to do this, they're not our biggest risk. But what this does do is this helps take out the noise level a little bit. It makes it a lot easier for us to see what's going on kind of with this baseline level of probing taken out of the picture. So then the next thing we do is the tiniest bit of math, and it's just addition. And this is that we score every request, and we figure out this IP score. So this is that part about we know the request history for an IP. So we take every request that comes into any of our applications, and we give it a score, right? So a 2.0x request to an authenticated part of our application, that gets you a point, right? A 4.0x, a 5.0x, something that's really slow, you'll lose some points. And the magnitudes here are totally arbitrary, right? Like there's no magic behind them, there's no science behind them. I don't have an academic paper to my name to point you to. But the point is that it gives us some indication of the relative risk of IPs so that we can start to understand who's a real user and who's not. We then take those per request scores and we roll it up into giving each IP address an aggregate score, right? We just take an exponential moving average. You get your reputation score. It's biased towards things that are more recent so that your past history still counts but less than what you've done recently. When we do this, you get a score that ranges from a +1, which is a perfect score, right? You only make 2.0x requests. You can go infinitely negative if you really want. And 0 is kind of our neutral point, right? We don't know whether you're likely to be a real user or not, but that's kind of the neutral point. So if I go through and I score, this is from last week, if I score all of the IPs that have hit us last week, about half of people have a really clearly positive reputation score. About 10% of people have a really clearly negative reputation score. And most of these are not people who are trying to hack us, right? If 10% of IPs were trying to hack us, I wouldn't even have the hair that I still have. These are mostly people who are running API clients that just got out of control and they forgot about, right? And we see a lot of that. And then the balance kind of fall into this area where we don't really know whether or not they're positive or negative. They're new IPs or they're IPs that have kind of a mixed history. Because our scoring was completely arbitrary, this distribution is completely arbitrary too, right? I can change the scores and get whatever histogram I want. And that's okay, because the point isn't that there's some science behind this. The point is that we have some indication of what's going on. So this is a look at our block history going back to before we were attacked. So until April of last year, we only blocked things manually. And typically what would happen is we'd see a problem, we'd go digging through logs to figure out what IP was causing the problem, right? And then we'd block that IP. And we did that for a long time. We had 2 big attacks before we started automatically blocking that were people who were trying to use botnets to brute force logins, I think using the LinkedIn list of leaked passwords. But that was kind of the history until last year. Then we started doing this auto blocking. And since then, you can see the pace that we've blocked people has really taken off. Of course, in any blocking system, there's going to be false positives, right? This isn't a perfect system. And so we do occasionally catch real customers who then write into us. The most common case is, I forgot my password and I was just guessing, right? And one failed password attempt isn't going to get you blocked. These are people who went really crazy at guessing. So we do occasionally get people who we do need to unblock. But overall, the vast majority, over 99%, we haven't needed to unblock. So the other thing that's a little bit different about our approach, right, which is all about kind of request history and these simple heuristics, is that we don't do this in the request process, right? This isn't something that, like one of these appliances, sits in your request stream. This uses byproducts. So we're big users of Kafka at Basecamp, and we love it. So we feed into Kafka kind of all of our request logs, the logs that the application generates, that the load balancer generates. All of our logs go into Kafka, right? All of our NetFlow data goes into Kafka, and then the data from Thread Exchange that we consume goes into Kafka. And then from Kafka, we have this request score, right? It reads the request logs and does this scoring that I mentioned. We have this scanner that looks at a bunch of logs and does this scanning for bad behaviors. And then we have a lot of tools for manual evaluation and assessment that we use pulling from Kafka. So to bring this back to kind of more traditional monitoring, so monitoring for a volumetric attack is pretty straightforward, right? And Eron showed these graphs earlier. The best indication that you're being DDoSed is when your network connection is fully maxed out. It's pretty obvious then what's going on. But you can also look at different types of flows. So we don't run a big DNS server operation. And so when we see a spike in incoming DNS traffic like we did about a month later, we know something's up. And in this case, it was the same attacker back again, right? He'd found an IP that we hadn't fully filtered. He hit us, we found it, we saw it instantly, we got a Nagios alert, and we dealt with it, and we didn't have downtime this time. What's harder than the volumetric attacks is these application level attacks, right? Where an attack is gonna represent some portion of your traffic, and there's no super clear indicator like your network is full. But what we find is that this average IP reputation score that I talked about before, again, totally an arbitrary number, right? It's pretty stable with an average around 0.7, but totally arbitrary. That could be 10 if you want it to be 10. But it's pretty stable, and it's very unusual in normal situations for it to fall into the negatives, right, for the average score to fall negative. And so we can look at this and say, this is an indicator of whether or not we're facing an attack. We can alert on this, and we can say, are we under attack? We were not under attack 2 weeks ago. I just broke something. So that's how we monitor things. The other thing everybody loves, this is an operations conference. I hear operations people like tools. So let's talk about the tools that we have that make use of Chicken. So here's a pretty typical scenario. So we'll get a Nagios alert. Warning, there's too many 4.0x errors on this site, right? Shoot, what's going on? So I just tell in our chat program, right, chicken me, right? And when I say chicken me, what's gonna happen is we're gonna go out and we're gonna find what are the riskiest IPs that have accessed us recently, right? And I'll get a list of here are the riskiest IPs sorted by risk score, right, that you might wanna look at to see what's going on. I can then click on any of those IP addresses and I get this report card, right? And we have this report card for every IP address that's ever accessed us, right? It shows what ISP they're from, what geography they're from, their request history, and then I can go and I can look at the actual requests that they made and go look at the logs of those requests if I want to. So I can pretty quickly get a really clear picture of who this IP is, what they're doing, what their user agents are, what their accounts are, what's going on with that IP address, so that I can make a decision. And then if I don't like that IP, I can go ahead and I can block that IP address, and WAFFLES will take care of the rest from there. Okay, so that's how Chicken works. At the end of the day, right, if we take a step back and we say, what is Chicken then giving to WAFFLES? It's 4 things, right? The first is this list of IPs that we should definitely block, right? These are people who we don't want hitting our application. We should block them, right? The second is a list of IPs that we should definitely trust, right? These are people who we know are really good, normal users. We don't want to mess with their traffic. We just want them to be able to use Basecamp. The third is a list of IPs that we're unsure of. These aren't people who we want to block. These also aren't people that we want to give a complete trust to. So this is the list of IPs that we don't know about. And then finally, when you pit Chicken with WAFFLES, you get a nice tasty meal, and I'll let Eron take it from here.
All right, so while Chicken is the brains of the operation here, WAFFLES is the brawn. So let's talk a little bit about how we got from where we used to be in terms of how we block malicious people to where we are now with WAFFLES. So we've evolved our approach based on these requirements that you can see here. Obviously, we want to be flexible in what actions we can take on this traffic. We want things to be automated. We want them to be scalable. And most importantly, we want the customer experience of these blocks to be as painless as possible for people who get inadvertently swept up into the system. So initially, back in the dark ages, we were doing this with IP tables rules on multiple HA proxy hosts that we had to put in there manually. These were less than ideal. You could only block traffic. That was your only available action. There was no automation at all. You had to log into multiple servers. You had to enter commands manually. It was error prone. It was always kind of a nervous experience. It was CPU intensive on those machines. IP addresses were the only thing that you could block. And maybe worst of all, the customer experience was bad. When these customers would come into this site, they would just get dead air as response, and that's never very helpful, especially when you get dead air from the help site that you would use to report this issue. So when we went and bought new load balancers, we moved this to that level of the stack, which was certainly an improvement. At this point, we could now block and rate limit bad actors. We had an API that allowed us to do blocks via chat in the slide that Noah showed earlier. But this was not exactly ideal. It was still CPU intensive on the load balancers themselves. And although we gained the ability to do a little bit more with the blocking units, the customer experience was still just as bad. You still just got dead air back. So when we upgraded our routers following the attack, we moved the ability to do these blocks further to the edge, which is always a good idea. You always want to block things as close to your edge as you possibly can. And at this point, we were able to both block and do some kind of rough bandwidth limits on IP addresses. We still had the API that we were able to use for blocks from chat, but we gained the ability to do the automatic blocks with chicken data that Noah talked about earlier. We got rid of our scalability concerns here, but the blocking IP, or the blocking unit, was still just IP addresses, and our customer experience wasn't any better. So eventually we've gotten to the point where we can use WAFFLES. And WAFFLES really addressed all of these concerns that we had. We get a trusted list, a block list, and a kind of a gray list for challenges that I'll talk about later. We still have our API and we have automatic blocks. WAFFLES can scale horizontally if needed to terminate lots of traffic. And we're able to block on IP, user agent, and path. And most importantly, people who get blocked, if they're paying attention to the block and they're not just a busted API script, they will get a nice friendly error page that they can do something with. So let's talk a little bit about how this works. So with WAFFLES out of the picture, our traffic flow is pretty normal. It looks a lot like probably most people in this room. So traffic comes from the internet, hits our routers, goes through our firewalls and load balancers, hits the application, and everybody's happy. So when we put WAFFLES into what we call penalty box mode, we're able to send known bad traffic away from our load balancers and down to the WAFFLES servers where they get this friendly error page. And trusted and untrusted and unknown IPs all follow the same path. They go through the firewall and load balancer, they hit our application, everything's fine. We can also run WAFFLES in proxy mode, where we send all of the traffic for a website through WAFFLES. And then we use our block list to send the error page, just like we would in the previous slide. Trusted IPs, those IPs that we know have good scores and are our good customers that we don't want to interrupt their experience, they get sent through the firewall and the load balancer to our app servers normally. But we also have kind of a list of IPs that we can't make a call about. Either they're new or we just don't have enough information about them to decide that they're definitely good or bad. And so those IPs we can issue any number of challenges to try to get them to prove that they're a real user with a real browser. So the WAFFLES hosts themselves, they live on their own traffic, or they live on their own network and they get traffic sent to them via BGP flow spec rules. This network is kind of off to the side and has limited access to our production servers. And the WAFFLES hosts are able to advertise themselves using BGP up to the router, so this is how the horizontal scalability part of this works. We're using an extension to the Border Gateway Protocol, which is a routing protocol that makes the internet work. This extension is called FlowSpecs, and it's a really powerful extension to BGP. Traditionally, it's been difficult to send flows of traffic based on source address in real time different ways in your router. And so flow specs are what allow us to take the list of bad source addresses that we get from Chicken and send them off to the side to be processed by the WAFFLES servers. And yeah, these flows can be defined either by the source addresses of traffic or the destination IPs of your website if you want to send everything for one website off into the Waffles hosts. So when traffic comes into the routers and hits Waffles, Waffles is really just Redis and Nginx. So from Chicken, we get several lists that we put into Redis. We get a blocked IP list and a trusted IP list. And in Nginx, we terminate SSL. We check for the presence of the IP in either the blocked or trusted list. If you're blocked, you get the block page. If you're trusted, you get sent through. If you're on our gray list, then you can get any number of these challenges. These challenges can be as easy as a 302 with a cookie, and if you come back with that cookie, then everything's good. Or you can get as complicated as you want. You can get as complicated as using like a client-side cryptography library to make them decrypt something and send it back to you. It's really all about how complex your attackers are and how complex you want to be. So this is the friendly error page that I've been telling you about. This is what it looks like. This is what customers see if they get inadvertently blocked. And so this is definitely improvement over what we had before. As I mentioned, our help site is hosted by us, so if you got blocked, you wouldn't get to the help site. Now you get this, which has a nice email link that you can click on to send our support team an email, and that email includes your IP address, so that makes it very easy for them to go into our systems, take a look and see what's going on with this IP, and if it's something inadvertent, then they usually get people unblocked within a few minutes, and they can go about their day. This is an example of a really complex way that you can do the 302 system. So somebody goes to this fictitious URL, you send them a 302 back to the exact same page with a super secret key and your IP address. And if they come back with that cookie set, then we send them on their way. So all in all, I want to leave you with 5 lessons that we learned on our attack day. And hopefully you can learn from what we had to deal with. Number 1 is that this isn't a cheap solution. It costs a lot more than 2 Bitcoins, but we think it's certainly been worth it for us, and it's much better than giving that money to the attacker. Number 2 is that good data and insight into who your users are going to be invaluable in building this kind of system and running your site in a better and more responsible way. Number 3 is that most of these commercial appliances that you can buy to do this kind of thing are really just black boxes. They're hard to monitor, they're hard to get information out of, they're hard to explain why they've taken the actions that they've taken, and in the end we were just unhappy with them. Number 4 is that you can definitely build on the shoulders of lots of great open source projects. What we've done wouldn't be possible at all without a bunch of projects, especially the Nginx OpenResty team, ExaBGP, Kafka, and a bunch of others. And number 5, sometimes you just need a whole lot of bandwidth. So thank you very much for having us.